So, hello everyone. Once again, thank you, Pedro, for introducing me. My name is Anja Jankovic, and it gives me an immense pleasure to be presenting you today what I believe is some of the most exciting research directions in our line of work, which is the automated algorithm selection and configuration. This is a joint work with Tome, Eftimov, and Carola Doerr. And to introduce you best to our work, I will first need to give you a tiny bit of background. So let's imagine we're presented with a problem that looks like this. We need to optimize it. It's a smooth problem, so we might as well choose a very simple algorithm to solve it, such as the local search, right? But then we might be presented with a different problem, which is a more rugged problem, and it's really highly multimodal. So local search is not a great choice for optimizing this kind of instance. So what algorithm should we choose in this scenario, right? So this is the topic that studies these kinds of questions, the per instance algorithm selection, which in a very short summary means that we want to select the best performing algorithm when presented with a new problem instance. A lot of research has been already done in this field by, for example, Kershke and the collaborators, Munoz Acosta and the collaborators on one hand. On the other hand, for some different standpoints, there are Hutter and Lindauer with their teams. And we also have many important contributions to this topic from related lines of work by many different researchers shown here. And so how does this, for instance, algorithm selection actually works? So in order to represent our problem instances well, we need to use appropriate measures to approximate the problems. Those measures are called features, and they are a part of a topic called exploratory landscape analysis, which was introduced by Mersman. So features actually approximate the fitness landscape of a problem. So the PS works by first sampling and evaluating search points of a problem in a first stage. Then we use those evaluated samples to compute the actual feature values, which will represent our problems for the selection part. And then we need to train, typically, because it's an automated algorithm selection field, we need to train a machine learning model, which will have as input some set of problems represented via features, and also a set of different algorithm performances on those problems. And as the last step, we will then use this ML model to, when presented with a new problem instance, be able to select the best performing algorithm for that instance. This, however, can be quite computationally expensive strategy, especially on one hand, because the training of the model itself needs to pay off regarding, for example, the performance of a default solver that we might just use to optimize some problem instance at hand. And on the other hand, even if we neglect that part of the computational difficultness, the also very challenging part is to actually need a lot of time and resources on our hands to actually evaluate, to perform a number of function evaluations that are very important to the optimization community. And in this first part, we need to actually reserve quite a lot of function evaluations only for the feature computation in the next step. So what we could do is maybe warm start the algorithm that we are about to run using those previously sampled points. This is one thing. But another thing, and it's the alternative or pretty straightforward solution we're proposing here, is to actually integrate that sampling part within the optimization process itself. So let's say we run our algorithm and we track and record the samples that the algorithm sees anyway and their evaluations for some budget B. In our case, B was 250 function evaluations. Then we those are the samples that we will later use for feature computation. Then we stop that recording. We let the algorithm finish its course. In our case, we give it another budget B of function evaluations, and that gives us 500 in total. And it is at that point that we predict the performance of our algorithm. So in a sense, we will use the search trajectory of the algorithm itself to be able to predict its performance at a later date. And not only that, but at this point of when we stop the recording of search trajectory, we also add as additional problem features the algorithm's internal state variables, which can give us maybe a better overview of how the algorithm looks like at that point to help further in the prediction of the algorithm performance. So this is basically summarized here in a few sentences, and just to note that we place ourselves in the context of a fixed budget optimization, which means that we have only a limited number of function evaluations at our disposal, and then the algorithm performance is not measured by the expected runtime, as typically is in the fixed target scenario, but rather by the target precision, which is the distance of the best found solution after that budget is after the budget, and the optimal solution of the problem. So some of the key questions that we aim to answer in the work are how different are the prediction accuracies when using those trajectory-based ELA features versus the globally sampled features, so versus the standard, the typical approach. Then how different they are if we use those ELA features, the search trajectory features alone, or would it help to add those internal state variables of the algorithm to the equation? And also, as suggested by many works in this field, sometimes the improvement can be seen if we perform a feature selection and if we use some carefully selected feature portfolio to do the same thing. So these are some of the questions that we aim to answer. So here we see in this plot the performances of our algorithm on different problem instances, and those are different runs of the algorithm. This is important only to show that there are some runs that are actually, even after the full optimization budget is finished, they're still quite far away from the optimum. This is a log scale, by the way. And then there are some that are really close to the optimum after 500 function evaluations. So this insight led us to actually train two different machine learning models because one, if we predict the performance on actual unscaled data, this would be better to aim at a larger target precision values, and the other model predicts the log performance data, which is aimed at better predicting fine-grained target precisions. And this is pretty evident because when the best found solution is already near, very close to the optimum, actually what is of interest to us is to just see the distance level to the optimum, which is expressed by the exponent of the actual data. And also we can combine those two approaches to select, to pick the best out of both worlds. And we can say, okay, if the log predicted target precision is smaller than some threshold, then we will pick the algorithm selected by the log model. Otherwise, we pick the algorithm selected by the unlog model. This is just a side note, but we add this question to our set of key questions to test in this work. And so just a few words about the experimental setup. The algorithm of our choice was the CMA-ES, which is a very powerful heuristic in continuous optimization. So we performed 20 independent runs of it. We computed our problem features, our ELA features, using the first 250 evaluated samples from the search trajectory. We computed them in the tool, in the R package called Waco, and there are 38 features in total. Then we record the internal state variables after we finish tracking the search trajectory, and we record the performance of the algorithm after our full fixed budget of 500 function evaluations. We have 5 internal state variables in total. So our problem benchmark, the problems that we test our approach on, is the well-known Bebop testbed on Coco platform that contains 24 problems. We consider first 5 instances of each in the dimension 5. And our regression models are just off-the-shelf random forest. And we perform 5-fold cross-validation, which means that we train on 4 instances and then we test on the remaining one. So just some results per question. So when comparing trajectory-based ELA features with the global ELA features, we see in this plot that they are actually quite comparable over most problems, although the global features still outperform the prediction quality compared to the trajectory-based ones. We use 2 sets of global features computed using 250 and 2,000 uniformly sampled points globally from a problem. We see that adding state variables to global features does not improve prediction quality. So the global features alone themselves are the most performing one, but the trajectory-based features are quite reliable also, as they can actually predict quite well the performance of the algorithm we have in question. So another thing we wanted to look into is what the advantage would be of if we add the state variables to those ELA features. And here we see actually this orange square is ELA features only, and this gray triangle is ELA plus state variables. And we see that actually we have only a marginal advantage of adding state variables to trajectory-based features. Although there are some problems, like for instance this problem 12 that had the smallest error when predicting using only state variables. Then the third question we had in mind is how good the prediction quality would be if we use different feature selection techniques. And here we use 4 different feature selection techniques in the scenario of transfer learning, one of which has 3 different values for the correlation threshold, which gives us a set of 6 here selected portfolios of features. And except in the case of RFE portfolio, we don't really see any advantages of using the selected feature sets in comparison to the original ELA plus state variables feature set. And lastly, how to combine unscaled and long models. So these results show the root mean squared error per function for all the different sets, excluding the feature portfolio ones, the selected feature portfolio ones. And for the combined model, and we can see here that the combined model, which is the orange square, is actually outperforming any of the standalone models across all problems, across all the different feature sets, including the selected feature ones, which just gives us a push to continue with this combining the model. Although per feature portfolio, we had different, because we performed ad hoc threshold optimization in this combining the models. For each feature set, we have a different best threshold value. So this is something that obviously needs further investigation. But the takeaway part is that actually predicting the algorithm performance using search trajectory data is actually quite good, and it actually works, although we are only in the beginning of our path towards some very open questions and very interesting things to look into. First of one being, can we use those trajectory-based features of some algorithm 1 to predict the performance of another algorithm 2? Also, how to capture the temporal component in the evolution of features and state variables, because for now we only use the state variables in the end of this search trajectory tracking, but it would be good to be able to record the evolution of them as well, and to maybe treat them as longitudinal data via recurrent neural networks or something like that. Then there is a question of how to optimally balance the budget of those function evaluations among global samples for feature computation, trajectory-based samples, and the optimization process itself, because we see that the global ones can still predict a bit better than the trajectory-based ones. So it's maybe worth looking into how to divide that budget so that we can optimize and save the most resources as we possibly can. Also, would form starting the algorithm with information obtained through global sampling help with an overall accuracy? This is something I mentioned in the beginning of the talk. Maybe it can calibrate the search directly towards more interesting regions of the search space. And there are some more feature selection and ranking techniques to be performed. Here we only use feature selection in the transfer learning scenario, but not in the same supervised task. So this is something to look into. Also, maybe the extension of feature portfolio, because there are many new features that researchers come up with almost all the time, and maybe there are some novel ones that can help better explain the interaction between the problem and the algorithm itself. And ultimately, can this approach actually lead us towards a powerful, dynamic, ELA-based algorithm selection model, which is our long-term goal? Will this trajectory-based approach be able to tell us, okay, now we know how the problem looks like, so and if we stop it at some point, can we use that part of the search trajectory to predict if we need to switch basically during the optimization to another more appropriate algorithm for that particular problem? So that would be all for today from me. Thank you so much. If there are any questions, don't hesitate. And all the details of all the results are really nicely explained in the paper. So I hope that you, at least some of you, are more interested to read it fully after the presentation. Thank you.
Thank you so much, Anja. It's a nice presentation, very clear presentation. So, anyone has any question? You can pose any question using the chat or or using your microphone. So don't be shy. Ask Anja anything you want. Okay, a quick question. In the chat, why do you choose CMA-ES?
First of all, we already did some previous research using the CMA-ES algorithm, and also we chose it as some clear choice, I think, because it is one of the most powerful optimization heuristics in continuous optimization. So we wanted to, which is actually very potent on all different kinds of problems. So even if the problem is very highly multimodal or whatever it is, it is very powerful and it optimizes the problems quite fast, I'd say. So this was just a clear choice, but we also want to extend this into adding more very different algorithms in our portfolio. Especially, I don't know if I can go back to a slide, you know, but especially here, because in order to have this dynamic ELA-based algorithm selection model, we will need to have a portfolio of diverse algorithms so that we can actually see in practice how this would perform and will another algorithm would be. So this is just a preliminary work to see if the approach would work, but of course we are open to adding more algorithms in the portfolio in the future work.
Okay, thank you. Just a short question. Among those 6 points of future work you I can see in your slide, have you tried any additional feature selection technique, or what feature selection technique do you plan to use next?
So we haven't thought about it yet. The only thing is that we want to test if the feature selection we performed now for this work, which is between 2 different supervised tasks. So we select the features based on the problem classification task, and we use those features for the regression problem we have at hand. But we also want to select the features within the same supervised task. There is still, those are all really open questions, and we dabbled into each one of them preliminarily, but I think that in the next few months we will have a clearer idea of what we want to, how we want to actually go forward with all this.
Okay, thank you. Very good paper, very good presentation. Thank you so much. Next presenter is Stefano Sarti.
Excuse me, can I just ask one last question?
Oh, sorry.
No problem.
Sorry. Yeah, please.
You said in the future work, in fact, I'm curious if you have any intuition about something. Can we use trajectory-based features of algorithm 1 to predict performances of algorithm 2? But what I'm curious is, if we compute features from the first algorithm, will we get the same features from the second algorithm?
I don't think so. Hi, Rafael. Yeah.
Hi.
Nice question. I really don't think so, because features can be quite unreliable and unstable, in a sense that each run of the algorithm, depending on the starting parameters of a certain algorithm, can lead us to completely different search trajectory of the algorithm itself. So it might happen that the algorithm starts from a certain point in the search space and has one trajectory, and the same algorithm even can have a completely different search trajectory even with the same uh, starting parameters. So what I would say is no, we wouldn't have exactly the same feature values, but yes, this is also maybe something to investigate further, whether those values could be similar enough in a sense that we can say for sure, yes, okay, we know that we're in this area of the search space or whatever it might be. But those are not identical, no.
What you said, if we repeat the process to make enough runs of some more, to have enough budget in our features, features from the first algorithm will tend to be similar to the second algorithm.
Yes, if we have that kind of a budget to perform that many runs, probably the average or the median value of those features would be the same. So here we also even for the global features, when we sample uniformly across all search space, we tend to get different feature values for the same problem. So what we did here is we performed 50 independent feature computations and we took out the median feature value is. I don't know if I'm replying to your question.